Okay, now we're going to look at hexadecimal or base 16. I should say that from the outset why we have to know about hexadecimal. I mean, we understand base 10 because we have our fingers, and we understand we need base 2 binary because that's what computers that's how computers work. They have electrical circuits inside them. It's either on or off, 1 or 0. So why do we need hexadecimal? Well, hexadecimal is sort of used by computer scientists to represent binary in a more human readable form. If you looked at a computer memory, you would just see ones and zeros, and even such a small number such as 256 requires 9 bits to represent it. So you can imagine looking at the contents of computer memory, you'll just see a mass of ones and zeros, and our poor old brains wouldn't be able to cope with it. So what we want to do is we want to encode that binary, or rather view it in a different way so that our brains can understand it better, and that is what we use hexadecimal for. So now let me explain what hexadecimal is. Well, this is, I'm going to put it next to base 10. Here we go, base 10. There's 16, base 16. I'm going to need 2 sides of the page for this. Okay, so as you well know, that in base 10 that means 1 unit, 2 units, 3 units, 4 units, 5 units, 6 units, 7 units, 8 units, 9 units, 110, 0 units, 110 and 1 units, 110 and 2 units, 110 and 1 3 units, 110 and 4 units, 110 and 5 units, 110 and 6 units. Well, base 16 doesn't stop at 10 before, you know, having a 10s column or a 16s column. It goes all the way up to 16. So we need characters to be able to represent 10 to 16, and we use A, B, C, D, E, and F. Let me show you. Okay, this means 1 unit, 2, 3, 4, 5, 6, 7, 8. No surprises there. 9. Now we can't put 1. We can't have a 10. It's not a 10. We still haven't got to our 16s yet. So we have to go A, B, C, D, E, F. Now when we get to 16, we have 1 in the 16 column and 0 units, just as we have with our 10. But because it's base 16, it goes all the way up to 16. So you'll think to yourself, okay, yeah, I understand. Rather than going from 1 to 10, we go to 1 to 16. But how does that help us? Right, let's convert some binary into hex, and I'll show you. I'm going to take a number. Here's a byte. 1, 2, 4, 8, 16, 32, 64. No, 1, 2, 8. Right, I'm going to take a number now. I am going to take the number 179 base 10. Now that is a 1, 0, 1, 1, 0, 0, 1, 1. Base 2. Okay, so if we saw that in memory, we would see 1, 0, 1, 1, 0, 0, 1, 1, and it would be like, oh my goodness. So what we're going to do is we're going to convert it to hexadecimal. The way we do that is we partition the byte into 2 nibbles. So this is the first nibble and the second nibble. And then we redo our 1, 2, 4, 8 on the different bit positions, but this is now a least significant bit in the different nibble. What do I mean? Well, here it is. 1, 2, 4, 8. It's not 16 anymore, it's the least significant bit in the second nibble, so that's 1, 2, 4, 8. And now we convert what we've got in binary into hex. So what we've got here is 1, 2, 3, so that's 3. And we've got 1, 2, 3, oh, 8. 8, 9, 10, 11. 11. Well, as we know from the previous slide, 11 is represented with a B. So rather than saying 11, we represent it as a B. So in short then, 179 base 10 is a 10110011 base 2, or B3 base 16. So the key is divide byte into 2 nibbles. Reclassify bit values. What do I mean? Well, here, for example, that's not 16, 32, 64, 128, it's 1, 2, 4, 8 now. And then 3, calculate value of nibbles. And 4, represent as hex chars.